Hello. We start now single variable calculus, really. I mean, we finished our lecture notes. Okay. Yesterday we have finished our lecture notes in the first semester, and now I have to apologize for, so there are no lecture notes for a while, right? In fact, Professor Pankratov, who gives to part of you seminars and also he gives lectures for second-year students, he prepared lecture notes, but at the moment he sent them just to me. Maybe he doesn't consider them in final form. I hope he'll complete this work in next future. So for a while still I'm using his lecture notes, but you haven't them yet. Sorry for that. And also his lecture notes, he didn't give the material sufficiently quick for our course, and that is why his lecture notes are constructed in slightly different manner. It means they're called integrals and series, but series are not included yet, at least. I hope he will do it in next future. But for a while we start integrals, and in fact our course, I mean single variable calculus, is devoted to integrals and series, first of all. That is our topic for this semester. And chapter 1 of this course, chapter 1, primitives and indefinite integral. Integrals. Primitives and indefinite integrals. Can you place somehow, because, I mean, in... Не, сменить. А зачем меня? А, хотя давайте меня действительно. Я хотел всех вместе, мозаикой. Я не знаю, если честно, как это сделать. Может, мозаикой? Никак? Так, вот вид. Вид докладчика. Что за ерунда? Давайте вид галереи. О, вид галереи. Ну пусть хоть так будет. Да. Okay. And we start with section. Yeah, you know, I used always numeration of sections with the help of numbers for lectures, right? And yesterday was lecture 30 of the first semester course, right? So now is lecture 1 of this semester. So numbering starts today, 1.1, and this is just the definition, the differential of a function. The differential of a function. So, what is it? That is, so denote the increment of the function y equals to f of x, which corresponds to the increment of the argument x, of the argument delta x at the point x naught by delta y. So, what it means? Look, we have an argument x, right? So, at the point x naught, we give the increment to the argument. So, we consider this change of the argument, right? So, instead of the point x naught, we substitute here slightly different value, which corresponds to this changing of the argument. So, and delta y, what is delta y? Is the difference between the value of our function at this new point and the value at x naught. So, once again, we give an increment to the argument and look at the increment of the function, how the function changes if we change its argument, right? That is the notation, nothing else. So that is just notation. Now, maybe I'll give it like a proposition. The function y equals to f of x is differentiable at the point x naught if and only if there exists a number capital A such that delta y equals to capital A times delta x plus little o of delta x as delta x tends to 0. That is the proposition. In fact, I would say that in most part of textbooks, that is the definition of differentiability. So if you look at most part of textbooks, that is the definition. But now we should prove this proposition. So, proof. Let me recall the definition of differentiability. So, when the function is differentiable? The function is differentiable if there exists finite derivative, right? This was our definition. So, differentiable. So, suppose f is differentiable. Then there exists finite y prime at x naught, which is equal to the limit as delta x tends to 0 of, the same, using those notations, we can write just delta y over delta x, right? With the help of our notations, that is precisely the definition of the derivative, right? Okay, put this as our number capital A. So we denote by A our derivative, in fact, right? After that, look, what we have to check. What means this equality? What means little o? What is the meaning of this little o? It means if I'll group them, so what I need to check, delta y minus a delta x, I need to check if this is little o of delta x as delta x tends to 0, right? That is what I want to check. I want to prove this, right? Now, look. What means this writing? Little o. By the definition of this little o, of this symbol, it means that if we divide by delta x, so this writing, by definition, has the following meaning. If we divide by delta x, then the limit as delta x tends to 0 is 0. So what is written, just I explain what is the meaning of symbol little o, nothing else. Now look, so that is what I need to check, right? So, look at this. What is written? It's practically the same, right? Delta y over delta x minus capital A. Here, right? So it means we have proved. It means this is proved, so this is proved as well, right? Conversely, let delta y be equal to a delta x plus little o of delta x as delta x tends to 0. So let it be, right, this equality. Once again, what is meaning of this little o? By the definition, that is this one. Right? This one. It's again just the meaning of little o. Then, what we deduce? Delta x over delta x we cancel, so hence there exists the limit of delta y over delta x, and it is equal to capital A. So we know it. And what is it? It means there exists the derivative, right? And it is equal to this capital A. In particular, it means that the function is differentiable, right? So, hence, y equals to f of x is differentiable. Differentiable. Okay? There are some. And we ask questions from lecture 30. Okay. Usually not a good idea to ask questions from other lectures. Little o is a symbol which was introduced some time ago. Okay, so proposition is proved. Proposition is proved. Now, that is very important equality. Let me write it down once again. So, now definition. Definition. If f is differentiable, at x naught, then the expression a delta x is called a differential. Differential of y equals to f of x. Of course, same meaning as here. I mean, delta x, x naught, they have the same meaning as it was in the main definition of notations and proposition, right? And now look, so also let us compute. So example. Notations. I forget about notations. So notations. Notation. A delta x equals to dy, where y is f of x. So that is the notation, right? So now, example. Y equals to x. Very simple function. Y equals to x. Then, what is about derivative? A is y prime. It is equal to 1 at every point, right? Doesn't matter which point. It is always 1. So what is differential then? Dy equals to delta x. And remember, y equals to x, right? So it means we have dx equals to delta x. So this particular example explains why usually there is a notation that, and that is notation, so notation. If x is an independent variable, then dx equals to the increment. So that is just the notation. So if x is an independent variable, then dx denotes the increment of this variable, nothing else, just notation. So what it means, now formula for the differential will be like that. dy equals to f prime at our point times dx. Right? And also, this is used as a notation for the derivative in many cases. And in fact, we did it practically when we computed derivative of a parametric function. Look, so once again, f prime at x naught equals to dy over dx, or y prime equals to dy over dx, right? Yeah. I remember when I started at the university, we have military preparations. These were different times, maybe. And one officer wrote that formula to us and said, "Don't cancel to D." So don't cancel to D. Right? Don't try to cancel D. Okay, so now, look, I think now it's a good time to understand geometric meaning of the differential. So, what is geometric meaning? Let us consider the graph of a function, right? So let it be here, for example. That is y equals to f of x, the graph of a function. So we fix a point, x naught. Now, as we know, if the function y equals to f of x is differentiable, we can draw the tangent, right? That is the tangent. Now look, suppose we give an increment. So that is an increment of the variable x, delta x. So here is the point x naught plus delta x. Then where is delta y? Look, what is delta y? Delta y is f of x naught plus delta x minus f at x naught. So f at x naught is here, f at x naught, right? So we need to compute our function at very large, let it be not so large, f of x, right? So that is, somewhere here is f of x naught plus delta x, right? So the difference between those values is delta y. So this is, that difference is delta y. So where is delta y? It's here, delta y. The increment of the function, which corresponds to the increment delta x of the argument. Now look, what is the equation of the tangent? The equation of the tangent is y minus x naught equals to f prime at x naught times x minus x naught. That is the equation of this line, tangent line, right? Because it goes through the point x naught f at x naught, right? Oh, f, I'm sorry, f at x naught, right? It goes through the point x naught f at x naught, right? And it has the slope f prime at x naught. The derivative is just the slope for the tangent, right? Now, look, we are interested in understanding what is geometric meaning of the differential. So dy, as we know, is nothing else but f prime at x naught times delta x, right? Where is it? This expression. But it's, look, if we consider this increment, so the increment of the tangent line, right? So what is the increment of the tangent line? Look, what do we have to do? Here is the equation of the tangent, right? So we should substitute instead of x, put x equals to x naught plus delta x. Then what we have? If we substitute x equals to x naught plus delta x, what we obtain? Y equals to f at x naught plus f prime at x naught times delta x. That is f at x naught plus dy. This is f at x naught, so this is precisely dy. dy. So what is geometric meaning of the differential? The differential is equal to, so geometric meaning of the differential geometric meaning of the differential. Dy equals to the increment of the ordinate of the tangent to the graph y equals to f of x at the point x naught, which corresponds to the increment delta x of variable x. So you see, look, We have our main point x0, right? We draw the tangent. Now, give the increment delta x to variable x, and what we see? The increment of the function itself, delta y, is here, and the increment of the ordinate of the tangent is the differential. So sometimes it is also, differential is called principal part of the increment. So you see, the main or the principal part of the increment of the function is differential. What it means? It means that the difference between them is not is little o of delta x. So, because remember the definition. Look now, once again, where is, not here. Delta y equals to dy plus little o of delta x, as delta x tends to 0, right? That is from the definition of the differential. So you see that this differential is principal part of the increment of the function. And what it means this one. Yeah? You see, so dy is the principal part up to terms which are little o of delta x, so larger powers of delta x. They are outside of differential. Okay, now properties of the differential. Maybe okay. In fact, we can collect many properties just looking to the definition. So look, what is differential? Derivative times delta x. So it means take a property of derivative, multiply by delta x, we have property of differential. That's it. So, properties of differential. Properties of differential. First, differential of a constant. What is it? D of c. What is it? 0. Yeah, because derivative is 0 and 0 times anything is 0 again. Second, differential of a sum difference. Differential of f plus minus g equals to what? What? df plus or minus dg, right? Once again, we just take a property of derivative and multiply by delta x. Third, differential of a product. Here it is a little bit more complicated because of properties g times df plus f times dg, right? Because of the property of derivative of the product. And maybe like a corollary, differential of a product of a function by a constant is equal to constant times differential of f. So we have linearity of differential. So differential is a linear operation with respect to functions. And the last property of this kind is differential of ratio fourth differential of a ratio. So I will write here f over g equals to, so remember property of derivative. Derivative of ratio equals to derivative of numerator times denominator. So it means denominator times differential of numerator minus f times dg over square of denominator. Of course, we should suppose something about functions. What is supposed? Here, f, g, and over there also, of course, are differentiable, right? Differentiable. And one extra supposition for the force, g not equals to 0. In fact, at the point where we compute differential. Because, remember, differential is computed at a point. Okay, but we'll consider it after break in more details. We continue. I have to answer to a question. So the question is as follows. Can we say that difference of delta y and dy is so little that it tends to 0? Look, this equality is still here, right? We can say more. The difference is so little that it tends to 0, and moreover, it tends to 0 faster than delta x. Right? So we should say even more than it tends to 0. It tends to 0 faster than delta x. Okay. Now, okay. So, we continue. So we looked at properties of derivative and we changed them into, in fact, this was very slight change. Just, you see, we multiply by delta x, nothing else, right? But there is one property which is essentially more important. I mean, property of derivative, which is essentially more important in this context. So, look, I would like to recall chain rule. Chain rule. What chain rule says? So if we have y equals to f of x, right, and x equals to, let's say, g of t, then we have a composition f over g of t, which is just f of g of t. Let it be h of t, that is y, right? And if both functions are differentiable at related points, I mean x naught is g of t naught, and f is differentiable at x naught, g is differentiable at t naught, then what says chain rule? Chain rule says that h prime at t naught equals to f prime at x naught times g prime at t naught, right? So you see this sign of composition, small circle, right, transforms into usual product when we consider the derivative, right? That is such a transformation, that is chain rule. Now look what it means for differentials. Look, we know what is differential dy. This is equal to f prime at x naught times dx at when? It should be delta x, right? And there was a notation, dx equals to delta x if x is an independent variable. That was a notation which was valid only for the case when x is an independent variable. So this equality now is not applicable, right? Because what we wrote before was written only under the supposition that x is an independent variable. Now, in this case, x is not an independent variable. X depends on something, right? X depends on t. X depends on another variable. It means we have no right yet to write it like that. Not yet. Not yet. What can we say about dy? We know y is h of t, and if t is an independent variable, then dy equals to h prime at t naught times dt, where dt is equal to delta t. So in this case we have, right, it is possible to introduce the notation dt equals to delta t. So dt equals to delta t. We take an increment of the independent variable t, right? And y is a function of t, and differential can be found by this formula, right? Now, look, h prime at t naught. We have a formula according to the chain rule, right? So let's continue this. What it gives, that is f prime at x naught times g prime at t naught times dt, right? But x equals to g of t, hence differential dx, now we may use this notation dx, but how to understand it? That is differential of a function, right? Dx is differential of this function. What is it? G prime at t naught times dt, right? Now we can use the definition of the differential. Look, it's here, right? So it means, it follows that we can write f prime at x naught times dx. So you see, I said to you, we have no right to write it like that, right? No possibility yet. I mean, because we couldn't use the notation dx equals to delta x, right? Because there was an agreement, dx equals to delta x, only if x is an independent variable. But it turns out that in spite of this, the formula is still valid, right? So no problem with it. You can write dy equals to f prime at x naught times dx, even if, like here, you see, forget now about this, right? But we don't care about this function, but we don't need to suppose now that x is an independent variable, right? So this formula for the differential is valid in both cases. Either x is an independent variable or x depends on some other variable, right? Doesn't matter. This property is called invariance, so maybe I should write it down explicitly. So what we have proved is called invariance of the form of differential. First order. I didn't use words first order yet. I'll use it a little bit later. So, what it means? The formula dy equals to f prime at x naught dx for the differential of the function y equals to f of x is valid in both cases. Either x is an independent variable or x depends on another variable. That is very important property. So we have proved it now, right? Using the chain rule. And now I should explain why I used words first order. So 1.2, differentials of higher orders. Differentials of higher orders. Or higher order or differentials. So, suppose x is an independent variable. Then, okay, maybe f is differentiable at x. Not x naught, just x. So now we'll vary x as well. Then dy equals to f prime of x times delta x. By definition, right? Yes. And you see, in fact, it means the differential of the first order depends on two variables. X, the point where we consider, right? And the increment, delta x. And both variables are independent on each other, right? So, but it means that we can consider, look, fixed delta x, right? Fixed delta x. Delta x is fixed. So we have a new function of the variable x, right? And we can consider differential of that function. Right? So by definition, second differential, which is denoted by d2y. Don't say d squared. No, never. d2y. That is differential of second order. Is differential of dy. Looks easy, right? But that is very complicated definition. Why? Because look, x was an independent variable, right? We fixed delta x. Now, we consider this expression as a function of x. We take its differential, right? How we should take differential? We need to take derivative of that function with respect to x, right? And to multiply by an increment. And this will be in general a different increment, right? So sometimes, I mean, what is generally, it should be like that. So we differentiate that function, right? We fix delta x. Now we should take an increment. Let it be, let's say, delta, small delta, little delta. So it means we should take like that prime times delta x. Another increment, right? In general. And if x is an independent variable, then in general we can, okay, delta is fixed, and we can write f double prime of x, delta x times delta x. But of course, there is an agreement. Don't try to consider different increments for different differentials, because it's crazy, right? We have the same letter here, D, so it's natural to consider the same increment each time. So, delta x is equal to delta x. Both increments are the same, by definition. And then look what happens. Then what is it? That is f second derivative at x times delta x squared, right? There is a standard way to write down. So notation. Remember that we denote delta x by dx, right? And using this notation, we have d2y equals to y double prime dx squared. Or second derivative equals to d2y over dx squared. I'm sure you saw this notation, right? For the second derivative. But now it is explained. And please don't mix, so in numerator 2 should be near d, and in denominator near the variable x. But be careful. This supposition now is very essential. For the first order differential, as we saw before, there was invariance, right? But now, for second order differential, no invariance. Why? Because, look, so consider the case when x equals to g of t, right? Like before, x equals to g of t, y equals to f of x, so y equals to h of t, just the composition, right? F of g of t. So now x is not an independent variable, but x depends on something. Look, if t is independent variable, then we know what is d2y. That is second derivative h double prime of t times dt squared, right? That is what we know by the definition of second differential if t is an independent variable. Now let's compute. So what is it? That is h prime of t prime dt squared, right? H prime of t, we know. What is it? That is f prime at g of t times g prime of t, and we should differentiate this expression, right? Now we have a product. So we have to differentiate the product. Let's do it. It is f double prime, no, not yet, sorry, f prime at g of t prime times g prime of t plus, okay, let me use other brackets, f prime at g of t times, okay, here Derivative of derivative is second derivative, not a problem. G double prime of t, dt squared. And look what happens now. Look at this. That is once again a composition. F prime composition with G, right? So again we need to use the chain rule here, right? So what we will obtain? I should take the derivative of outer function, f prime, and it gives second derivative. So f double prime and g of t times derivative of inner function, it means g prime. And we had another g prime, so it means g prime of t squared. And I want to open brackets, so times dt squared. Plus a second term, let it be like it is written. No problem. So f prime and g of t times g double prime of t dt squared. Now look, t is independent variable, right? Hence, second differential of x equals to g double prime of t times dt squared, right? And first order differential dx is g prime of t times dt. That is because t is an independent variable. Now substitute both expressions. What we'll obtain? F double prime at x times, here you see, square of this one, right? So dx squared plus f prime at x times, and that is d2x, second differential of x. Now compare with the formula for the case when x is independent. It's different, right? Essentially different. So you see, this part is the same as for the case when x is independent variable, right? And we have extra term, d2x, which contains d2x. The formula will be the same, by the way, in a particular case. When? When this formula is still valid, even for dependent variable x. This is still valid if second differential is 0, right? But when second differential is 0, second differential is 0 means second derivative is 0, right? And second derivative is 0 when the function is a linear function, right? So it means that still the form of the second differentiable is invariant, but only in the case when x is a linear function of an independent variable, right? I will not formulate it as a proposition because we'll use it next year for several variables. But for a while, just it's first time when it appears, right? Okay. Also, to finish this section, look, we considered differential of second order, and of course, for the case of independent variable, we can proceed further, right? So by induction, by induction. And differential is defined as differential of the order n minus 1, right? And once again, every time we should take the same increment of an independent variable. So we have several operations of taking differential, and every time we should take the same value of increment of the independent variable, right? So, and look, if we'll proceed like here, so then by induction, we can easily prove that this is equal to nth derivative times dx power n, right? But that is only for the case when x is an independent variable, of course, right? Otherwise, it is not true. And look, so another form, so notation, or maybe not notation, so d n y equals to y m dx power n, or nth derivative is d n y over dx power n. So here it is not power, that is order of differential. That is why the place is different. Here it's just power of dx. Once again, why should small delta x and capital delta x be equal? Why should? That is just to be not crazy, nothing else. Because in general, yes, you are right, we should consider them different, right? If we proceed in logical way. But that is just to make things a little bit simpler, that's all. So every time when we consider the differential, it's natural to take the increment the same every time. That's all, nothing else. That is why we take them equal. And by the way, it explains also why, so if x is not independent, then delta x, we have no freedom in the choice of delta x anymore, right? Delta x is the increment. If x depends on something, then its increment also depends somehow, right? So we have no freedom in the choice of delta x. That is why, in general, we cannot do it like that. And that is why no invariance for the second differential, and of course no invariance for higher order differentials. You can imagine we have only two terms for the second differential, and for differentials of higher orders, of course, there will be essentially more terms. And still we have invariance for linear functions x, right? That is a particular case when we have linear functions. Okay. Now, I think that's all what I wanted to say about differentials of higher orders. Now, it makes no sense to start new section. So, there was a question about, let me have a look. can you tell us at the last minute of this lecture about our program for this semester and grading scheme? Yeah, good question, good question. I should tell you, but I can't at the moment. So, in fact, most probably, there will be a written exam in analysis, but still I cannot say definitely. I asked for a written exam, but you know, it depends. You see, your session will be smaller, so it depends on other exams, how many exams you have. So still I'm not sure if it will be it will be possible to do it simultaneously with other exams. In fact, you see, as far as I understand, it was completely impossible to make written exam in calculus during winter session, right? Because part of you had written and oral examination in physics. So the whole week. And you had just 2 weeks. That's for exams. So I don't know yet. We are discussing those things with other. So you see, there are too many sides here which are involved. I mean, different departments, I mean, schools, right? You have different specialities, different exams, other exams, I mean. That should be discussed, and we are still in the process. And of course, this is the main question, right? If there will be a written exam or not. The grading scheme depends on it, definitely, right? And also, you know, for standard, I mean, Russian students, this system was created many years ago, so everything was prepared in essential time before, but you are the first, how to say, the first collection of students in such conditions. I mean, before, there were very few students. So just one teacher gave lectures, gave seminars, so he gave everything, and so everything was not formal. Now, because of different teachers in seminars, right? Of course, everything should be done with common denominator, right? And you see, even after the first semester, there is different rate with different teachers, right? Although, from the beginning, we had the same program, but nevertheless, somehow, you know, because of, once again, people, now they have another habit. They taught before in one manner, now things are essentially closer to general scheme of studying at our university. So you are essentially closer to usual students here than students before. That's it. Main reason. But still, you see, we have some problems because of this. So we are working on it, and I'm sorry that, yeah, but about the program, yeah, good question about the program. In fact, I wanted to give you the program together with topics for seminars, but maybe I can do it without, because I prepared just a list of topics which I plan to cover during lectures. That's it, right? And that is ready. But the detailed program for seminars is not ready yet. So maybe I'll inform you about the program at least for lectures. That is what I can do, definitely. Yeah. And there was another question, just a minute. Derivative sine is cosine, what is it? You gave us the meaning of the differentiation, but for example, what is the geometrical meaning that derivative of sine is cosine? Poof. Geometrical meaning that derivative of sine is cosine. It can be explained somehow using parametric formulas, but I don't think I need to do it, because, yeah, in general, I mean, just for sine and cosine there is some geometric meaning of this, but I don't think we need to consider it essentially now, because we go further. So now we'll start indefinite integrals in next. In the book we can follow with the lectures. As I said, there are lecture notes by Leonid Pankratov, so here they are, but he sent them to me only yet. I don't know when he will consider them sufficiently ready to be published, let's say, right? That's it. I'm sorry that I didn't answer to all your questions. I mean, organizing question, in fact, you are right, perfectly right. It should be done, definitely, but I'm sorry. That is because now you see, you are in some sense first students with those problems. Students before had no such problems of that kind. Sorry. Okay, that's all for today. Thank you.